So, hello everyone. We've been hearing good presentation today, mostly technical, and some of them is related to mistakes and human factor in structural engineering. So my paper is amplifying what Gordon has previously conveyed about the human factor in structural engineering. Mistakes does happen in what next? As a structural engineer, I usually question myself, what is the concept of being a structural engineer really? What do we do in our daily life? And it comes up, we learn the scientific base and then we implement it in our daily work, like material, strength, stiffness, deflection, and all of that. And along the experience, along the year, I start learning about the art of engineering. For example, load path. We start being creative, how to create an efficient structure, the appropriate ductility that we choose in our structure analysis. And we combine the science and the art part of engineering into ourselves as a human. And we also know that we do our daily work to meet the client constraint, which is the limited time budget, to meet the certain quality or standard being outlined by the code and standard and also the client requirement. But with all those pressure, sometimes it's stressed a lot to us in giving high pressure to our daily work. And most of the time, as a human, we are likely to make mistakes. How do we prevent, or not even prevent, how to minimize the human mistakes in our daily work? In 1997, I think this Swiss cheese model has been brought up by Gordon previously. James Reason, a UK scientist, he kind of put a model that resembles a Swiss cheese. And then his model is very suitable for indeterministic failure pattern. What does it mean? So indeterministic means the failure pattern that is heavily with statistic and probabilistics. So we imagine and we know our work in daily life, we are working with very heavily statistic and probabilistic, like material strength. Do we really know the characteristic strength of material that we are designing? Definitely not really. We accept between 5% to 95% percentile as characteristic strength. And also like loading, seismic loading, wind loading is all based on statistic. And the workmanship, how many tests that we specified in our specification to make sure the workmanship is really good. So all of them are very statistic heavily in our daily work. So this system-based failure model, the Swiss cheese, is very good, I believe, to prevent or minimize the mistakes to become losses in our profession. So if you could imagine, you thinly slices the Swiss cheese and stack them together. So there is potentially the whole of the Swiss cheese may not align together. By putting all this prevention layer, we try to filter the hazard or like the mistakes that we do in our daily life to become losses. But as perfect as it seems, when the holes are aligned together, the losses are still happened. So in New Zealand, we put all this prevention into our system. So the first layer, probably like self-checking, technical review, peer review, the consenting process, the authorities' approval, and construction monitoring. But again, like when the mistakes pass through all those holes, it still becomes a losses. So what can we do if the mistakes happen? So the mistakes can happen in various levels as a structural engineer. It can be in the micro level, which is in the individual. It could be as simple as put a wrong number in the calculator, or we've been talking about confirmation bias during the analysis, and even omission, assumption. All of those could be happen in micro level. And in the meso level, we've been talking about how a constant long working hours in the management or in the culture of a company. And then in the macro level, it could be like a loose regulation. You guys may know the leaky building that we faced in Auckland. So yeah, some mistakes can be acceptable imperfection, or it can be the catastrophic, unacceptable errors. But again, mistakes still does happen. And what to do if we still do make mistakes? So there are 4 psychological stages in human, like when we make mistakes. The first one for sure, like we feel embarrassed. I'll be honest here, like we all feel embarrassed when we do make mistakes. And the second stage is denial. So, like at this stage, there are lots of conversation in your head. Even sometimes like we blame others for our mistakes at this stage, which is not good at all. But I would like to emphasize here at this stage is really good to keep your mind open, listen to others without defensiveness, because by doing so, we learn together as a profession. And then the third stage is regret. Sadly, this is the step where the people find it hard to get up and face the mistakes. But this is an important stage so that like we remember our mistakes forever and we will not make the same mistake again. And the last one is the acceptance. I believe the best apology is not by word, but the best apology is by the commitment in showing the client our willingness to fix the mistakes. And as individual, if we go through this process, like each of us doing this process and being regret and acceptance, and start the sharing our knowledge to the other people, so that like they open mind during the denial stage, I believe we will avoid the blaming culture in our profession, and instead we nurture what we call learning culture in our profession, and we can grow together as a profession. So, but let's see what happened in the past. So in 1981, this was categorized as the deadliest non-deliberate mistakes in the structural engineering history. So there were 2-story walkways spanning on an open atrium at the Hyatt Regency Hotel, and the 2-story walkways just collapsed onto an ongoing tea party. It was very catastrophic, and it caused 114 people death and 216 injured people. So what actually happened in here? So on the right-hand side, the design engineers put original design as an intention, like a sketch as an intention of the work connection from their perspective, and you could see it's a concentric connection, and the two walkways is being supported with a continuous anchor rod through the roof. But during the construction, the contractor just noticed that it's not practicable to install it on site, because if you could imagine, you have to install the fourth level of the walkway through the continuous anchor rod, and you have to screw the bolt and the nuts continuously from the second one to the fourth floor. So it's very impracticable from their perspective. So instead, they had like a phone conference with the design engineers, and they said they would like to modify the design. Without seeing the proposed sketch, unfortunately, the design engineer approved the modified design. As a structural engineers, we know how we avoid eccentric connection. By generating those eccentric connection, apparently the walkway itself cannot support its own weight. And unfortunately, it collapsed during the ongoing tea party. So there are certain lessons learned from these mistakes. During the investigation, they notify there are micro level of mistakes, which is the design engineer put something on the paper that is impracticable, and also approving something without reviewing the design, and doing a verbal approval, which was quite unlikely around this like current practice. And in the meso level, the design engineer defend themselves, saying they constantly working for a very long hours during 1980s because of the construction booming at that time. And it was very unfortunate. And also the macro level, they noticed the practice at that time was unclear. Who's responsible for the modification during the construction? Like, whose responsibility does the engineer needs to go on site, do like inspection, and give like a updated sketch or something like that. But I'm amazed how the profession embraced the learning culture during these mistakes. The Jack D. Gillum, who the owner of the company, he claimed full responsibility of the mistakes. He said like he didn't review the modified design properly, and then he shared his mistakes through conference, through academic lectures, so that like the young engineers can learn from him. And the profession also update the curriculum in states. They put the ethics of engineering and also emergency management. So I could see how the profession embracing the learning culture to make a better profession in the future. So thank you. I just want to say for all the engineers who made mistakes or are going to make mistakes, we are in this together. The way we fix the mistakes is going to fix our reputation as well, to gain the public confidence to us. We owe it to ourselves and also the public to act as in professional and responsibility. Thank you.
Thank you, Vini. I think it's really interesting to see how what you're talking about is tying into some of the bigger themes we heard this morning. Our next speaker is Phoebe Moses. Phoebe is a chartered structural engineer with Beca based in Tamaki Makaurau. For the past few years, much of her focus has been placed on growing Beca's offerings in the structural sustainability arena, developing tools and design guidance to assist the wider team in delivering sustainability-related work. She is about to take a 1-year hiatus from work to complete a Master's in Environmental Sustainability in Scotland, learning from the UK's experience in the sustainable buildings industry. Phoebe's paper is on the topic of integrating sustainability considerations into structural engineering and includes some interesting case studies in a New Zealand context.
Tēnā koutou katoa, nā mihi nui ki a koutou, kua huhui mai nei I tēnei rā, mō te wānanga me te whanaungatanga. Thank you to everyone here who's come to learn and connect throughout the conference. I'd also like to acknowledge Waikato Tainui Iwi and Kingi Tu Hetia Paki. Also, I just was reflecting on it before in the other session that it's pretty special how during this time of Matariki, which is really all about Te Tau Hou, the new year, where we look back and we reflect on the last year and then plant the seeds for the next year looking ahead. So I thought that tied in quite well with the whole CSOC conference. Today I'll just be touching on a few of the broader topics of sustainability, and in particular drawing from my experience in the last few years helping clients deliver their sustainability goals, essentially. I've just popped a couple of sustainability frameworks up there. Sustainability is many things to many people. It doesn't really matter which framework you use so long as you remember that the most important thing is to not focus exclusively on one aspect to the detriment of all others. Most of you are probably familiar with the 3 pillars approach of social, environmental and economic sustainability. There are heaps out there. Just as with any tool, use it with a grain of salt and make sure you're using it properly. I've summarised where I think the main benefits that structural engineers can provide in the sustainability consulting world into 8 different topics, which if you want to look in more detail, they're in my paper, but I'll just be briefly touching on them today. I think, most of what we have to offer falls within this. You may be familiar with some or all of it already in the context of your work as a consulting structural engineer, but I'm going to approach it with a sustainability lens. Before we dive into that, I just want to put the spotlight on carbon for a second. Now, carbon is a very topical topic. What we mean when we talk about carbon is the effective carbon dioxide emissions from a wide range of greenhouse gases, which is typically expressed in tonnes of carbon dioxide. Now, why is it important to structural engineers in New Zealand? Well, our government's actually committed to a decarbonisation pathway under an internationally binding agreement, the Paris Agreement, that we have to meet. And not only that, but we've got our own national legislation, the Zero Carbon Amendment Act, which we are also beholden to. So there are many reasons, both legislative and moral, why we need to be thinking about it. I've popped up the graph there, which is our decarbonisation pathway towards a net zero 2050 future. Think of it as a carbon budget on a carbon credit card where you can go ahead and spend a whole lot of it now, but the repayments you'll end up making years down the track will be much more difficult and larger to implement. In the context of buildings, I've stolen a graph from ThinkStep's report a couple of years ago on embodied carbon. All the blue lines are the carbon associated with the physical parts of a building, and the green are the operational parts. As you can see, a huge proportion of the embodied carbon sits in those really early design life stages. So I've tried to frame up the rest of the presentation as a series of prompting questions, which I hope will spark a bit of thought and perhaps debate. Do feel free to come and discuss and argue with me at any point throughout the conference. The thing I'd like you to remember is that questions which are asked early on in design are the most important. Even by the time we've got to the end of concept design, a lot of the main opportunities will have already passed us by. So with that in mind, I'd like you to consider this quote up here by Dr. Mike Cook, who actually, this was in response to a question that I asked at the iStructD Gold Medal address last year, which was trying to get to the centre of the structural carbon debate, which, for those of you in the know, is Is it more important to focus on upfront carbon emissions in early life cycle stages, or should we approach carbon from the building longevity and resilience aspect? His answer took no time at all, but bear in mind he lives in the UK where earthquakes aren't really a thing, so that might have tied into his answer. But I tend to agree with him. The climate emergency is now, therefore the changes that we make in the short term are a whole lot more important from a sustainability carbon perspective. There are other perspectives out there. Right, number 1, material reduction. You might be familiar with this graph or graphs like it. It's essentially highlighting what I was talking about before, that the decisions you make at those really early design stages are what's going to have by far the biggest impact. Obviously, the question, do we need to build a new building, should be asked. We're lucky in New Zealand that we've got a really rich history of seismic strengthening, so we've got the tools and expertise necessary to, in most cases, be able to retain existing assets, and we should where possible. Optimisation of structural sizes, while still important, is definitely far less impactful, and that's really what you're limited to if you think about carbon during the later stages of design. Oops, how do I go back? There's more to material selection than cost and whether or not it can span from X to Y. I definitely put in the last slide, have those conversations early on with your architects about building layout and structural form, because you don't want to be locked into a certain way of being or a certain material selection or structural layout just because of some performance requirements. There might be other ways to achieve those performance requirements which give you more flexibility in the design. So yeah, I've put up a little spider diagram there, which I've found is quite an effective way of communicating different structural pros and cons to clients. Any sort of tool like this, a matrix with pros and cons. The most important thing in my mind to communicate to the client is that we want to be using materials where we make the most of their strengths and where we avoid their worst weaknesses. I am not going to go into a debate right now about the relative merits of steel, concrete and timber. There is plenty of meat in that discussion, which I'm sure will be touched on probably next door, actually. I know Jared's going to jump into that a bit. Material specification. We typically don't look at our specification as a means of obtaining sustainability, good sustainability outcomes, but there's a lot of examples out there which can help us to incorporate some of these things into our specs. What I would think is the most important thing is to have, again, conversations early on with your contractors. What's achievable? What's a stretch goal? What is way out there? Because there's examples of all of those in some of these specifications, and we should really be taking the easy wins where we can. I know I said before that reducing carbon now is the most important. That doesn't mean that we shouldn't focus on what happens to the building later in its life. Adaptive reuse is a really powerful way of, repurposing a structure. We don't want to get to the point where the only viable option for a building is demolition, and we can really help provide future people with good options if we think about it early on. So through redundancy, just thinking about possible changes of use. Don't limit yourself and build a sloping deck car park, which might just need to be demolished even before it's built. Resilience has been a bit done to death, so I'll just gloss over it with that sustainability lens. From a carbon perspective, which is only one aspect of sustainability, obviously the longer a building is in existence, the lower its annual effective carbon impact will be. So yeah, we do want to be designing our buildings to be up there a long time, if at all possible. Designing for reoccupancy is really important, so those earthquakes that come along that are perhaps less than ULS, and I know it's been talked about a lot already this morning, provide a high level of protection to those non-structural items so that you don't need to throw things out and re-put them in. End of life and deconstructibility. Now, everyone likes to say, we've designed our structure to be deconstructible or demountable, but the reality is you've got little to no control over what happens to a building at the end of the life. The best thing you can do is just make sure that you've provided the option for someone to make the best decision at the end of life. But really, you've got to assume worst case current demolition approaches. Social license applies to a huge range of things. I've just touched on two aspects here. Firstly, have we considered the principles of te tiriti o waitangi in our design process? We don't tend to think about ourselves as structural engineers as having a lot of agency in this space, but I've recently worked on a project with a council who had a really strong positive relationship with their local hapu, and one of the first things they asked for was for us to be able to partner with that hapu, and I learned a lot through that process around partnership and participation, and that was a really great learning curve for me, and I would highly recommend everyone to not exclude themselves from those processes. You know, if you've got a planning team or an architectural team, get on board, do the learning, and you'll gain a lot from it. Secondly, have we considered the local community in the area where our capital project is being built? Whenever we've got a project that's in a remote or inaccessible location, we do think about those things. We think about the local labour and resources available. We should try and apply that mindset, in my opinion, to all capital projects. We saw during the COVID crisis how we were really able to positively impact the local economic community through supporting local business, and I think we should be aiming to do the same for capital projects. Holistic design is really just acknowledging that your structure doesn't exist in a silo. Again, the key to figuring out how we can have the best positive impact is to have those conversations with experts in building services, architecture, fire engineering. You know, are we providing enough thermal mass? Can our structure provide solar shading? Trying to tie these different things in together is a sustainability, for good system sustainability outcomes is pretty key. Jumping into, I've just got 2 minutes left, so I'll just spend a little bit of time on these case studies. Again, feel free to come and chat to me if you want more information. Firstly, AUT A1, so on Auckland's Akoranga campus for AUT, we have designed a 4-storey LVL moment frame timber structure, which is sort of tied into 2 existing buildings which are being strengthened. So what enabled us to make and put a real strong focus on sustainability through this is that we had an engaged client who had strong sustainability goals. And this made us get quite creative, especially in the reporting of the process and communicating to the client how we were making decisions. How did those decisions back up their sustainability goals? I had a go during a pre-concept of reporting against the United Nations Sustainable Development Goals. It was interesting and maybe not something I'd do again, but there are different, other frameworks out there that you can report against and are quite well set up for you to think about. And there's a lot of information out there that's available to us. My second example is the University of Auckland. This project actually started out as a more or less maintenance and refurb with an idea of quite a limited 15-year design life. But the university, in conjunction with the design team, soon realised that there was an opportunity here for us to really invest in the building and project that out to a minimum 50-year design life. So give the building a new lease on life, don't put demolition into the plan, think holistically, think sustainably. In conclusion, I've put a few of the main prompting questions up there. It's really just don't assume that sustainability is someone else's responsibility. Take up the torch, so to speak, and get involved. There are a myriad of opportunities for us to be involved, and there should be no reason why we don't jump at those. Thank you.
Thank you very much, Phoebe. I think it's really important to remember that there's a lot more than just optimising a section size when we're having sustainability discussions. So moving on, I think we've had one already this morning, but after Gordon Hughes's presentation on the impacts of human factors on engineering, we have another timely presentation from Michael Geddes. Michael is a structural engineer with 6 years' experience at WSP in Wellington and is a founding member of the CSOC ESE committee. His presentation is titled Mental Health in the Structural Engineering Profession.
Thank you, Laura, and good afternoon, everyone. I'd like to preface this talk by saying that I am by no means an expert in mental health. It is a complex topic, and this talk is just one angle on it. I would also like to acknowledge Gordon's excellent presentation on human factors earlier today. The World Health Organization defines mental health as a state of well-being in which every individual realises his or her own potential, can cope with the normal stresses of life, can work productively and fruitfully, and is able to make a contribution to her or his community. Sorry. I'm sure you will agree that as structural engineers we make meaningful contributions to our communities, but our work is not without its challenges. We're constantly making tricky decisions and judgments, perhaps more so than the average professional. Mental health is not merely the absence of illness. It can be helpful to view mental health as a continuum such as this one, rather than a binary state of healthy or ill. The current reality is that most of us will experience a mental health issue at some time in our lives, or be in close contact with someone who experiences mental illness, be it a long-term condition or relatively short-term. Indicators of mental health issues are not character flaws, weaknesses, or just a phase. The first topic I'd like to talk to is the transition from study life to working life. In my opinion, graduate engineers are particularly vulnerable to stresses as they begin to navigate the challenges of consulting, such as project deadlines, staffing shortfalls, and challenging team dynamics. Our 20s are a time of change, of joining the workplace and finding our place in life. According to Ministry of Health data, New Zealanders in their 20s feature highly in the use of mental health services, second only to teenagers. So just a bit about my story. In 2015, I moved to Wellington to start work as a graduate engineer. Really enjoyed it. In my second year there, we had a lot of work on. We were doing multiple large buildings, including a hospital, a hotel, and a school. One of our senior engineers, who was also mentoring me, unfortunately left us to return to the UK. That left me feeling a bit out of my depth. Unfortunately, I never really spoke to anyone about this. To use a metaphor, I had a cubicle mentality. I thought that these managers and senior engineers were far too busy to talk to me, so I thought I'll just put my head down and soldier on. And I can tell you that that is never a good idea. Eventually, my confidence was so shot that I had to take weeks off work, and I was seriously giving up structural engineering. But I got back thanks to the great support of two managers. I now know that no matter how busy a manager may be, you can always approach them. After all, it is their job to support you. Now, the metaphorical opposite to this is the collaborative workspace on the right of screen. I love the banter, just the day-to-day discussion at my work these days. And often the solutions to problems will come out of casual conversations rather than formal meetings. I always laugh when someone comes to me with, quote, a stupid question. There is absolutely no such thing. So, any graduates, I encourage you to always ask for help when you need it. Myself, I make a conscious effort to take an interest in our graduates and to make myself accessible to them. And to any seniors in the room, you are probably doing this already, but I just encourage you to keep making yourself accessible to your younger staff members. Which brings me to the whiteboard. So I have this anecdote, courtesy of Carl Ashby. I am told that Peter Smith, Distinguished Fellow of Engineering New Zealand, would hold whiteboard brainstorming sessions, which would make people groan. But it was a way of involving everyone from directors to graduates in the Curly problems. Maybe you, like me, have struggled with indecision in your work. The good news is that we can always get in front of a whiteboard and draw ideas from each other. And just know that you are never alone in your work. You are with a company that stands by you, and no one should ever work individually. Onto the coffee cup. I love this quote from my employer's mental health plan, which goes, "Something that we can all do is look out for our co-workers. Just think about their mood. Is somebody feeling down? Does it look as if they're struggling on a project?" It's tremendously powerful to engage with somebody and say, "Are you okay?" Or, "How are you feeling today?" The plan suggests to go and have a cup of tea or coffee with someone to help them articulate where they are at. Then if there's greater concerns, we can get help in place to support them. Communication, in my opinion, is one of the keys to ensuring well-being in our workplaces. Our day-to-day interactions set the tone for the office and provide support lines for when things get tough. My team at WSP tries to go out for a coffee each Monday morning. I believe that the more we take an interest in our workmates' lives and develop rapport, the easier it will be for them to come to us with their problems, be they work-related or personal. In conclusion, as structural engineers, we're subject to challenging decisions and circumstances that can affect our well-being. Graduate engineers are also subject to the challenge of transitioning into the workplace. I'd also like to acknowledge what John here said briefly earlier, that the graduates he is seeing are highly trained, but perhaps haven't had the feel for the craft of it. There's certainly a period of 2 or 3 years, or maybe more, where it's a steep learning curve, right? And I think we, as organisations, we need to do all we can to develop our graduates and support them. There are a number of techniques available to us for our well-being, and I've just scratched the surface of these today. For example, Engineering New Zealand in the past year or two has put out some excellent interviews and other things which are available on their website here. Members of Engineering New Zealand have free access to the MAS Wellbeing portal, and Engineering New Zealand also has a series of videos on transitioning from study to working life, which I can recommend. I'd just like to acknowledge CSOC for providing a scholarship for me to present here today. And with that, thank you for your attention.
Thanks for your presentation, Michael, and thank you also for being so open with your own experience. I think it's a really good reminder that you need to check in on the people that you're working with and creating groups, whether it be within your company or coming along to emerging structural engineers. Getting the chance to talk about how everyone's doing is really important of what we do. So we'll now hear from Ben Exton. Ben has worked as a structural engineer for both Structex and Building Resolutions in Christchurch since 2016. He has a keen interest in innovation and earthquake engineering, as well as improving communication through the implementation of digital technologies. Ben is presenting today on a project which combined both these interests, the New Brighton Pier earthquake repairs.
Kia ora koutou. Today I want to draw out some key takeaways from a project that I was privileged to be a part of a few years ago. A lot of you have probably been to the structure in Christchurch. I've tried to draw them out in a way that they're transferable to not only temporary works projects, but also it should give you some thought-provoking points on permanent works design and things that you can really take back to your own projects. But first of all, I want to start with a whakatauki, and it should hopefully help you reflect throughout the presentation. So it's ka rongo, ka wariwari, and that line is I hear and I forget, and then ka kite, ka mahara, which is I see and I remember. And there's another bit to come. So a little bit of background on the project. So it's the New Brighton Pier out on the coast from Christchurch is a really core part of the local community. It performed exactly as it was meant to, as far as I'm aware, during the quakes. It sort of is a single degree of freedom structure in the across direction and was severely damaged, but the people who were on it were safe, despite it moving about half a metre in all directions. There's some videos on YouTube of the action going down, so I encourage you to check those out if you're interested. There was some real discussions around whether it was going to be kept or repaired, and ultimately it came down to a really big community push to get the structure back in action. This is some of the damage that was occurring about 6 or 7 metres below the water surface. So you can see some pretty classic plastic hinging. And as you can imagine, being in such a corrosive environment, that creates massive issues for long-term durability and also the, subsequent strength for following aftershocks and future seismic events. The council had a permanent solution that they designed in-house, which was quite innovative and creative. However, there was a real challenge as to how it was actually going to be carried out. And so they funded 3 or 4 contractors and design teams quite a substantial sum of money to propose some creative concepts for the implementation. The design team that I was involved in was with our firm in Fulton Hogan, and it involved some large caisson cofferdams, which were designed to create a dry working environment for the people working within the breaking wave zone. So the design waves being up to about 5 metres tall, although at that point we were going to have people well out of the activity zone. We had the added complication that you're not only repairing a structure, but while you're repairing it, you're making the pile about 4 or 5 times the diameter. So considering the effect of wave loads hitting something far larger than the superstructure was designed for, how can we protect something for the future if technically it only has to be designed to a 6-month construction design working life. So in this case, it was actually designed to the full working life of the superstructure. And then how do you get those pieces of steel underneath such a complex structure? So you can see quite a complex arrangement of gantry rails and sort of rollers and systems for actually getting the equipment under the pier. Now I want to go to the key takeaways. So this project, and it goes back to the whakatauki, that you can tell someone something as much as you want and they'll probably forget it. So the best way is actually to show people, and then they might remember it a little more clearly. So this was, as I say, a few years ago, and the BIM renders have come quite a long way since. But BIM is a lifesaver for communicating with all different parties within the construction phase. So this was contractors, scaffolders, we had structural steel fabricators, everyone around the table trying to identify health and safety risks and potential clashes to keep the project moving. So I really encourage you to use BIM as much as you possibly can. It gets you out of a lot of trouble. One of the roundtable discussions, we actually identified that it was quite an expensive thing to fabricate, but by having the bolting sort of flange accessible from the exterior of these caissons meant that we didn't have to have anyone inside the danger zone while these caissons were live, swinging under chains with potentially waves hitting them. And another example of the communication tool was looking at different excavators and different equipment and making sure that the equipment that the contractor had procured could actually do the job. So rather than getting 6 months down the track and finding that we had to make some quite substantial changes. One of the things I really enjoyed about this project was the things out there that were kind of came at the curveballs that came along every now and again. So as you can imagine, back in back when you're a kid playing with water tubs and toy boats and whatnot, bathtub stuff, you learnt about buoyancy, and that applies really in this case. So if you have a large volume of water that you're displacing, you create quite a substantial buoyancy force. When our design team ran the numbers on this, it became clear that it was actually right on the edge of putting a net tension into the concrete piles. So not such a great thing for an asset that you're trying to retain. So setting some limitations around what the differential water levels could be, and how that protects the structure for the long term. Another thing is thinking about when you're designing your structures, thinking about long-term remediation strategies and how remediation will be carried out. So in this case, the access or the pier itself was designed for full HN loading, but the access ramp could only basically take a ute. So creates quite a challenge when you're trying to get a rather large wheeled excavator up there. So we had to have a crane pad and the knock-on costs and timing associated with that. So really thinking about start to finish, what does your structure, what's it going to see? Likewise with the concrete, some similar challenges, but if we ran a 300 metre concrete hose down the pier, we would have had a huge amount of concrete wastage every pour, and there was about 20 different pours. So given the weight limitations getting onto the pier, we had a big concrete truck pumping into a mini mixer, which would then cart it down the pier. So minimising wastage and minimising the risk of substances going into the environment. One that I think we tend to forget as engineers is that in the contracting game, the teams are often quite, people come and go quite often. So if you're having critical discussions around health and safety especially, within 2-3 weeks' time, it might be a totally different crew. So this was an example out on site one day where some processes were clearly not being followed, but I realised that those guys weren't there when we had the discussion the week before. So coming up with strategies for retaining key knowledge within a team is all part of the duty we have as engineers. And this is another one which was actually a failure due to those conversations not being passed on. So in this case, overnight, when we had no one working on it, we would basically let the bars, you can see 2 bars coming down, we would let those go, and the caisson would be allowed to sit under its own self-weight. And that was to stop the waves throughout the night eroding around the pile and causing them to become a big pendulum and basically batter into the pier. In this case, someone forgot to remove the plates and let it drop overnight, and so it became a pendulum and created quite a bit of secondary damage which had to be remediated. So it was another key reminder about having those core discussions and having them regularly. One for me was when a contractor might come back and ask for more construction tolerance, think about the ramifications of your, I guess, any concessions that you give and communicate any concessions clearly. So in this case, we had some fixed props to hold the caissons off the pile, and the contractor asked to put some adjustable lengths in, which are indicated with the red dots there. Now, it was quite crucial that we still had some fixed props. What happened in reality was that the contractor put in 4 sets of pin props, and we had ourselves a mechanism basically which created some, as you can see, some quite mangled looking pieces of steel and a bit of a challenge to get it out again. So communicate any judgments and concessions clearly. This was quite a nasty Saturday morning for me. I got a phone call saying that there was we had a couple of them actually. One was a tsunami coming through from Chile, and then the other was Cyclone Gita, which came through. Although there's a scaffold failure here, this was well communicated with the client. So communicating those environmental risks with the client and what they can expect if there is an event over and above what your design level was intended to see. This one in particular was accepted because the scaffolding was not crucial for the temporary works. It created challenges for the subsequent weeks because there was a couple of pieces of steel that had to be recovered. So some warnings out there for the surfers. All pieces were found. And then the final one, which is really just a lesson around bimetallic corrosion. And this was one of the strangest things. It was this ladder here is an aluminium ladder, just like you'd get at Mitre 10, but it's been strapped to about 5 tonnes of steel in a corrosive environment for about 3 weeks. And it basically just breaks off. So we're tossing up whether to send that one back for a refund, but thought better of it. So just going back to the whakatauki, so I hear and I forget, I see and I remember, and then the last one, I guess, is I do and I understand. So for a lot of these things, it wasn't until we actually got out on site that we started to understand the true complexities of what we were dealing with. So I really encourage you to think about those concepts along with the ones that I've spelled out, and hopefully they help you at some point. Thank you.
Thanks, Ben. Clearly some pretty unique challenges and also some unique communication approaches. So next up we have Hamish Tocher. Hamish is a graduate engineer at Holmes Consulting based in Auckland. He came to engineering from a background in fine arts, having worked as a lecturer teaching photography, art history and studio practice. While at engineering school, Hamish ran a heritage society, connecting engineering and architecture students and undertaking site visits to retrofit projects on heritage buildings in the Auckland region. Hamish and his co-author Matt Cutfield have worked on a number of assessment and strengthening projects for historic buildings, including projects based in the Netherlands. Their paper proposes a simpler approach to strengthening unreinforced brick masonry buildings in New Zealand.
Ngā mihi nui ki a koutou. Hey, it's the kind of time of day when minds start to wander, so I'd like to invite you to let your mind take a wander for a minute. And let's imagine that we bunk off early and go on a road trip. Now, we're going to miss the conference dinner, so maybe we'll stop in a little town somewhere for a sausage roll. So we're pulling off the highway and into the main street, and I want to stop you there, and I want to ask you, what does the main street look like in your mind's eye? And I imagine it probably looks something a little bit like this. As structural engineers, we probably recognise that those 1- and 2-storey brick masonry buildings are likely to be earthquake-prone buildings. But when we look at that same street on an aerial map, we get a little bit of a different sense of the scale of the problem. This is Fielding, and each of those orange dots is an earthquake-prone building listed in the earthquake-prone building register. And you can see a real cluster of earthquake-prone buildings in that downtown commercial area. But it's not just Fielding, it could be Levin, it could be Gisborne, it might be a little town like Martin, which is too small to have even got their buildings onto the register yet. It could be Waipukaro. We could have jumped down to the South Island to Waimate, or we could be close by in Huntly. So I hope I've just given you a little sense that in small towns up and down New Zealand there are a lot of earthquake-prone buildings. So the way we manage those buildings in the New Zealand context is through the Earthquake-Prone Buildings Amendment Act. And what we ask owners of buildings to do is manage each of their buildings individually. So there's a multi-phase process through which they do that, which involves an initial assessment and some more detailed assessment. It involves a design in multiple phases, often and involving different professionals. Then there's a consenting phase, and all that has to happen before a construction contract can be let. So some consideration was given to the costs that are involved with that process when the earthquake-prone legislation was formulated. And the regulatory impact statement noted that the costs for that would fall on building owners. And it also noted that the benefits would accrue to building owners, but would also accrue to the general public from the reduction in potential harm. So let's have a look at how that's played out, particularly in the context of regional New Zealand. I'm going to skip through this quite quickly for the sake of time. I really want to point out that both before the Act and also since the Act was passed, the research has tended to show that the costs that are associated with that multi-phase process we were talking about tend to drive owners towards having to make a decision to abandon or demolish their buildings, not in every case, but in a lot of cases, and in particular in regional New Zealand. So there's some studies both before and after the time of the Earthquake-Prone Building Act. I chose this one in particular because it talks about some of the consequences of those decisions to demolish or abandon and what they might look like in some of the small towns, changing previously vibrant provincial city centres into unattractive places. So there is a bunch of research, and I'm going to skip past that quite quickly. And in fact, some of MB's own work recently tends to back that up. So if we look at projecting what we think the outcome of that current policy setting around the Earthquake-Prone Building Act, if we look at projecting what that might look like in a little while, we see that some unreinforced masonry earthquake-prone buildings aren't going to get retrofitted by the deadlines that are contained in the Act, and that those ones are likely to be the lower value buildings which are concentrated in our regional centres. So if the owners have a limited ability to repair those buildings, it's a fair conclusion to draw that they're also likely to have a limited ability to replace those buildings. So we might expect that those places are going to lose a considerable amount of their historic heritage, but also their social and cultural amenity and just the livability of those places. I think another important consideration is that if the cost of embarking on the strengthening process is too high, we don't actually see safety improvements being made in the interim. So while those earthquake-prone building deadlines are running, it isn't, those structures in those towns are not getting safer. And to some extent, we can kind of see this happening in places, for example, in Masterton, in the Wairarapa, where the Empire Hotel demolition has led to an increase in homelessness because this was the transitional housing for that community. So I tried to kind of highlight very quickly that the Earthquake-Prone Building Act imposes some costs on owners of buildings, and that if we choose the current settings we have around the Act, a likely consequence for some of those buildings is going to be that they'll be demolished or abandoned, and that might be concentrated in regional New Zealand. So another possible option is that the government funding to help strengthen those buildings could increase. There are currently some funds like Heritage Equip, which offer assistance to owners of buildings. But that might put us in a situation where, as the public, we're asked to fund the improvement of private assets. And so there might be a limited appetite for that as a solution. So I want to talk about what engineers can do and what we can offer to make the strengthening of earthquake-prone buildings simpler and how we can maybe help to ease that problem. So the opportunity that we have in New Zealand is that our unreinforced masonry buildings were built within a relatively tight time frame between roughly the 1880s and the 1930s. The details of those buildings are all relatively similar, and the details are relatively well understood. And there's been quite a bit of research and testing which has identified some of the critical failure modes that we expect from buildings that are constructed in that way. There are also a bunch of standard retrofit details that exist, and MB has published some of those details after the Kaikoura earthquake sequence. So an option, and the option that we present in our paper, is that we allow non-specific retrofits to be applied to earthquake-prone masonry buildings without specific engineering assessment, and that we do that for some buildings. So I want to try and explain what a non-specific strengthening program would look like, and we call it in our paper simple strengthening. I thought if it really is simple strengthening, I should be able to explain it to you in one slide. So for simple strengthening, we would always restrain or remove chimneys and parapets, and we would repair canopies if canopy repair is required. We would always enhance the roof-to-wall and floor-to-wall connections, and I think that's a critical part of any strengthening program for an unreinforced masonry building, whether that's under the Earthquake-Prone Building Act or whether it's some other kind of strengthening. We would sometimes strengthen our walls out of plane with the addition of timber strongbacks, and there's some research and testing which supports that as a method. And we would sometimes strengthen diaphragms with ply, but we would also give consideration in our program to the effect that you might see in, for example, a row of buildings, and how you could consider the aspect ratio of the diaphragms of those buildings as a row rather than individual diaphragms. So the intent here is to provide a program which is non-specific, and it's somewhat analogous to the kind of thing that you see in 3604 or in 4229, where it's intended to be applied by the construction professionals, but it doesn't necessarily have to have the specific input of an engineer. So the intent is to develop some lookup tables that make that easy, those kind of things easy to apply. And I've noted that that MB have published some details which would require some further augmentation. So what kind of buildings does this proposal apply to? Jason Ingham and Alistair Russell did some work in 2010 identifying 7 different typologies of masonry buildings in New Zealand, and we propose to apply that to buildings within typology A to D, which is, say, 1- and 2-storey buildings. It's not really intended for more complicated structures like churches or things that might have larger diaphragms or irregular shapes. We intend to, or the paper suggests that the option here is to identify the buildings that are eligible for this treatment through a value criterion. And that's a kind of a rough way of measuring the financial ability for owners to generate revenue to strengthen or to replace those buildings. So one way to do that is to come up with a number related to CV. And another way to do that might be to follow the process in the post-Kaikoura time, which is actually identifying specific streets or specific areas for which this scheme might apply. So I live in Onehunga in Auckland, and Onehunga looks like any of those country towns you might have imagined stopping for a sausage roll in. But I'm not really thinking that Onehunga would be an example of the kind of place you would do this, because there's real pressure for apartment developments in this part of the city. We might have to give up these shopping streets and replace them with something else. And I think that the development opportunity, broadly speaking, is there in that kind of place. So we would, however, limit, as I said, the application of this program to buildings with specific geometric constraints. No weird stuff, nothing too irregular. So to briefly think about costs, the Earthquake-Prone Building Act and some of the research around that identified the costs of strengthening. And you can see from the numbers up on the screen there that there's quite a wide range of possible costs that were identified in that process. There has also been some research around a simple type strengthening and the kind of cost reduction you might expect to see. And some of that comes out of the United States, where they had a program called Bolts Plus, which run in a number of cities. And we make brief mention of that in our paper. So there are some numbers suggesting that you could get between 30 and 70% cheaper strengthening with a non-specific style scheme. Of course, that depends quite a lot on how you implement that scheme. So it's also important to think in our option that we target our spending towards the things that are most likely to cause risk or fatality, bearing in mind, for example, that in Christchurch the rate of fatality was 5 times higher outside those masonry buildings than it was inside those buildings. So people who've been involved with the strengthening of unreinforced masonry buildings will probably have noticed that there wasn't any in-plane strengthening in the scheme, and we have in fact excluded in-plane strengthening from what we're proposing here. While force-based analyses of in-plane capacity of masonry buildings may sometimes make them appear as though they are quite fragile in that direction, they sometimes don't always capture the full capacity. And when you look at them with a more sophisticated analysis, you can sometimes see that those structures are more resilient in the in-plane direction than it may at first appear. We also believe that buildings in rows have some ability to support each other, particularly once their connections and diaphragms are strengthened. Of course, there's quite a lot of caveats to add to that, and it's worth saying that any simple strengthening scheme of this type would need to be developed with robust engineering principles in mind. So a word about percent NBS. Our current method for dealing with earthquake risk is to use percent NBS as a method for capturing the performance of the building and also the risk that the building might pose to occupants or to passers-by. And it relies on an engineering analysis that we do at the component level of the building. There's not really any sort of shortcut way of doing it. We need to understand the structural response of the building in some level of detail. And we also need to be prepared to be liable for the judgments that we've made around the capacity of the building. So NBS is appropriate for many, many circumstances. However, if we accept, and what I've tried to show here is that there is a class of buildings in New Zealand that will actually not receive a specific analysis and strengthening scheme, and those buildings particularly concentrated in regional New Zealand. If we accept that these buildings are not going to receive a specific design scheme, and we accept that doing nothing and allowing them to be demolished, or increasing the funding from central government is not a preferred option, then it may be possible that we can accept that simple strengthening, a non-specific style scheme, makes buildings and people safer without seeking to quantify exactly how much safer through an NBS style process. The intention there is that rather than a multi-phase process, without NBS involved, we would be able to get rid of a detailed assessment phase. We would be able to reduce the design phase through looking at the standard details that have been published. The consent phase can also be simplified by the use of pre-qualified details, and that we might be able to get from identification of buildings as earthquake-prone to a construction contract situation with a lot less time involved and less money. So there are a number of issues with the scheme that we propose, and I'm sure that you're thinking of some now as you sit. The removal of specific engineering input is a big issue. A robust, non-specific scheme is required in order to mitigate against potential vulnerabilities that may appear. It's also possible that it might create the perception that there is a different performance expectation between what we expect in cities and what we expect for safety in rural communities. I just want to say in defence of that if we're in a situation where rural communities cannot afford to strengthen their buildings at all, that a differing performance expectation may de facto already exist. So we need to bear that in mind when considering such a scheme. It's potentially an issue that we might have an uneven application of such schemes, and we would need to think about how the territorial local authorities can be supported to inspect or identify such buildings. And it's also potentially an issue that we might have this escape route for unreinforced masonry buildings because we understand the properties and failure modes of those buildings better than perhaps we do with some other structures, and the solutions may be simpler. So there are a number of other issues, and I'd just ask you to refer to the paper for consideration of those. But in summary, I presented some research that showed that in small towns there's a risk that unreinforced masonry earthquake-prone buildings may not be strengthened by the Earthquake Prone Act building deadlines. It may be possible that we see large-scale demolition and abandonment. I just want you to remember the map in your mind of those towns and think about what happens with all those buildings gone. An option is to allow a standard detail strengthening to be carried out with the expectation that that might lower cost and it might therefore increase uptake. And the suggestion is made that the determination of NBS on a per building basis might not be the only way to effectively decrease the public risk. Thanks for your time.
Thanks, Hamish. I think you've raised some pretty interesting issues, certainly made me think twice about my own hometown's fate. I think we've run out of time for questions, so again, this might be another questions on the bus scenario, but we'll try come back to it if we have time. Our final speaker for this session is Amber Coulthard. Amber has 6 years of Christchurch-based experience designing multi-storey structures. The earthquakes and the industry response have had a formative influence on her career and approach to structural design. Amber is passionate about providing practical design solutions and improving structural knowledge for sustainable building materials. Her paper uses the Ashburton District Council Civic Centre as a case study to share learnings on timber connections.
Thanks, Laura. Hi, I'm Amber Coulthard, a structural engineer at Beca, and I'm here to talk about the Ashburton District Council Civic Centre, a timber building. I've been involved in designing various multi-storey buildings in my career so far, and like many of us, a consistent factor of all of them is steel. Being involved in a timber building design has led to an interesting challenge for me. This presentation is intended to be a summary of some key learnings for timber design from the perspective of a designer more experienced in steel. As has been a focus this morning, we've been taught that as engineers, we should know the answer before we dive in. With timber structures, connections drive section sizes, layout to a greater extent than other materials. With less built examples, less industry resources, and more variability in timber materials, most engineers don't have the gut feel on what makes a timber connection work and what it needs to look like and what just does not work. Design resources and codes are more in flux, leading to a challenge of knowing what code to use, what material values to use, and what manufacturing possibilities there are. For a bit of background on the project, the Ashburton District Council Civic Centre is a series of buildings located at Baring Square, Ashburton, and it houses the town's library, council offices and a civil defence facility, the EOC. This project initially had a steel concept which limited intrusion of lateral structure and allowed for flexibility in the architectural spaces. The project went to public consultation, and my simplified interpretation of those outcomes was the community wanted more, they wanted sustainability, and they wanted timber. The design team went back to the drawing board and entered concept design with these new drivers. Just quickly on the design team, Beca carried out the structural, building services, civil and fire. GHD were the geotechnical engineers, Athfield architects, and PTL brought their timber experience as the structural peer reviewers. The project is made up of 4 structures. Out front is Building 1, which is the main focus of this. It's a 3-storey structure housing the library and council chambers. Building 2, out the back in green, is a smaller, seismically separate version of Building 1, housing more of the library. Then we have Pioneer Hall, which is a facade retention of a heritage hall that will sit inside an atrium which is attached to Building 1. And out back, the EOC, which we had as a single-storey IL4 timber-framed building. This is a typical cross-section of Building 1. The timber is the primary material with alveolar beams and columns, a podius panel floor system, CLT walls, and glulam for all the external structure. Steel and concrete were brought in when the structure moved outside the uniform layout that was required to make timber work. And this included a concrete floor topping due to the broken diaphragms around atriums, steel columns around the double height spaces, and steel for stairs and canopies. The lateral system for the building is post-tensioned CLT rock-in walls with dissipators at the ends for some extra damping. A challenge for these walls is the compatibility between the rocking timber structure and the gravity structure connecting to them. The ideal solution for this compatibility would be to put a troop in there and make sure that the walls and floors can move separately. However, this is really hard to achieve and has its own issues in reducing diaphragm connectivity and everyday serviceability performance. As this project did not have a low damage requirement, we focused on providing economic and robust connections, which built in redundancy, and we investigated the consequences of large rotations. The post-tensioning level was one of the key factors of the analysis. And for this, we needed to find the sweet spot between over-tensioning the walls and ensuring the walls didn't start rocking on a windy day. As the post-tensioning layout was critical to the analysis, we needed to figure out the construction methodology for this early. We worked with CLT suppliers to develop this, and here is a sample that the supplier put together. To do that, they will remove ducts to create the ducts, they remove laminars in the CLT wall during manufacture, and so we'll have these nice big ducts down the middle of the walls. Including the timber suppliers in this conversation was very important, as their laminar widths and lengths were all changing, and it was important to make sure we could actually build this. I'm going to talk through my key takeaways from timber connection design. I know most of us are aware of these ideas in some form, but it's easy to underestimate the importance of them, as we're able to just make it work in steel when we're caught in a bad design situation. Timber is weaker than steel. This doesn't mean it isn't a great building material, it means that we need to make sure we are using it right. I'm just going to stop quickly at timber codes. New Zealand standards are currently in transition, with no single standard really covering everything that you need to know for timber. More so than other materials, the designer needs to understand what timber material they are using and whether the code is appropriate for it. New Zealand's current cited standard is from 1993, and engineered timber products have changed a lot since then. A draft standard is out, and this is an adoption of the 2010 Australian standard with some edits to make it more suited for New Zealand and updates. A fire portion of this standard, 1720.4, was published in 2019, but it's not yet cited. And finally, we have the Eurocode, which is a lot better developed, but we need to be careful using it, as timber over in Europe is very different to timber in New Zealand. I think a timber designer needs to be across all these and various research. A big first step for New Zealand would be to get up to speed, would be to publish and cite a more up-to-date code. I watched a webinar series early on in this design by Wood Solutions, which among other topics talked about some of the basics of timber. One item that stuck in my head was that timber is like a bundle of straws. That bundle of straws is now how I visualize timber when I'm going through material and connection design. Timber is stronger parallel to the grain, just like a bundle of straws if you push down on the ends. Perpendicular to the grain, if you squeeze the straws, it's quite weak. As a rule of thumb, I don't try to carry significant loads through timber perpendicular to the grain. Engineered timber materials are a build-up of sawn timber or thin laminars of timber glued together in different orientations. And these different orientations mean that every timber product has its own quirks of parallel and perpendicular behaviour. Making timber projects work, and thus timber connections, is primarily about getting the building approach that suits timber. At concept stage, we have an opportunity to influence this and get the design team on board. With steel, we like to funnel the entire building's loads through specifically designed connections into a discrete lateral load system. Timber really doesn't play nice with this concentration of load. With timber, we need to operate on smaller and more consistent grids with lower loads transferred through each connection. Here are two early concept sketches that we provided to influence building layouts. The one on the right, the steel, was when the building was in steel. You see, we didn't show any structure, we just focused on building separation and diaphragm separation. When we moved to timber, we focused on the requirement for a repeated grid with significant walls that the layout would need to work in with rather than the other way around. And here is the final layout that we had. As you see, we managed to maintain the consistent grid in one direction. We allowed some flexibility in the other direction by making sure that in building one, a third of the blue walls were in each quarter. Overall, looking back, I think we should have pushed for more size in our vertical structure, wall length and column size. We thought we were generous with the sizes, but in reality, the sizing was just enough and led to more complex connections. Don't underestimate timber sizing required to make connections work. Another item that wasn't captured fully at concept stage was thinking about splices and cantilevers. In order to get longer spans and cantilevers in steel buildings, we rely on the ability to provide continuous members with backspans through welding. With timber, we're limited to the lengths of timber that can be supplied in New Zealand, which does tend to change sometimes. And we can't easily make a timber beam continuous through another one, so picking your primary beam direction is critical early on. This project, we have piers of 900 by 180 LVL beams, which sound really big, but compared to some other timber buildings I've been looking at, aren't actually too big. If it was a single beam, it would be a 1.2 metre deep beam. And if it were in steel, we could make a 530 UB work. So this leads to my personal rule of thumb for structural depth for converting from steel to timber is just double it. Again, capacities perpendicular to the grain are significantly weaker than parallel, so make sure your primary load paths are going through the good direction. Long-term factors have a huge effect on timber for both members and connections. One of my most surprising moments in this design process was determining the compression capacities of my CLT walls. I'll use the 2 metre long by 310 wide walls as an example. First, you apply the strength reduction factors and long-term factor, which brings the capacity down to 40% of the unfactored capacity. In CLT, you only use the vertical laminars for this compression, so take off another 50%. And then, to make the post-tensioning work, I needed couplers down at the bottom, so I cut out a hole which took away another 20% of the wall, which leaves about 18% of the original capacity, or equivalent to a 250 UC. So while these two sections have very different structural purposes, this comparison helped me understand and communicate the limitation on the level of post-tensioning we could put through these walls. Finally, after all this, connection requirements are probably going to drive timber sizes anyway. I'll quickly just fly through some things which, if you're going into timber, you should really have sorted. Don't mess up your fixing spacings and edge distances. These do lead to smaller fixings, more of them being a better option. And while you're doing that and spacing your fixings apart, make sure you don't space them too far apart, perpendicular to the grain, or your timber's going to crack. So, in summary on timber connections, don't underestimate their complexity and the amount of design and drafting time that they're going to require. Every connection needs to be considered. No WP30 is making life easy here. So, I have not been able to brush the surface, but some key takeaways. Use the right codes and guidance, and encourage the industry to get up to date on this. Know your materials. Regular layouts with more smaller connections, and within the connections, more smaller fixings. And finally, fire. The new 1720.4 requires protection of steel connectors and timber joints by one of the following methods. Embedding the steel under char depth, which for this project was 45 mils. A fire-resistant protective insulation covering, or fire resistance testing. A key item here is the insulation covering is required to have a 300-degree limiting temperature, which really pushes designers to embedding. These requirements are particularly onerous, so fire requirements can drive connections and layouts. Fire should be a primary consideration, and the approach should be discussed between the design team as early as concept design. Timber is a fantastic product with many advantages over other building materials, particularly from a sustainability perspective. With the global sustainability drivers, we want to see more uptake of timber in major structures. Designing with timber requires a shift in approach and a questioning of all your key assumptions. It also requires a design team to get on board with what makes a timber building work. As an industry and individual engineers, getting up to speed with timber design and keeping up to date with what's possible in the New Zealand timber industry is a challenge, and a key first step is getting that timber code done, and also getting more understanding and getting more clarity from the timber suppliers of what they can do. The more we design timber buildings, share our experience with each other, and work together as an industry, the more successful we will become. While designing with timber is a challenge now, with more experience, our industry can make timber a competitive product for commercial designs. Thank you.
Thanks, Emma. And before everyone runs away to buses, I just want to take this chance to say thanks again to all of our presenters. I know it's not easy as a younger engineer to get up in front of your profession and share your own experience, so I want to thank you all for the courage you all showed in sending us in papers. Congratulations as well to the ESE members who all earned scholarships to be here, so we really want to thank them for their involvement. I'm going to piggyback a little bit on what Paul mentioned earlier in his keynote, that our network really relies on emerged engineers, shall we call them. We really rely on you sharing your wisdom and your knowledge with us. So in that note, I'd ask that everyone bear that in mind and think about whether you've got a lesson that you can share, a project experience, technical experience. Please do reach out to us or your local reps. We'd really appreciate it. But otherwise, I think it's been awesome to see the range of topics that have been presented here, and I hope that you all are going away with something new to bring back to your own workplace. Enjoy the rest of the conference.